Thank you for coming to our session. We are going to be discussing energy transitions, land use, and land cover change with examples from the real world and the modeling world, mostly focused on Southern and Eastern Africa. The session was organized by my colleague Pam Jagger and myself. I'm Rob Bailis, senior scientist with Stockholm Environment Institute, and I will not introduce the speakers. I'll let them introduce themselves. Our first speaker is Dr. Kate Beach from Harvard School of Public Health. Please continue. And we're going to try and keep sessions to, or individual presentations to about 15 minutes. We only have 4 people, so that should allow plenty of time for Q&A. We'll take maybe 1 or 2 clarifying questions after each presentation, and then hopefully have a discussion after. Take it away, Kate.
Okay. Thanks everyone for coming here after lunch. As Rob said, I'm Kate Beach. I'm a postdoctoral fellow at Harvard Center for Population and Development Studies. I just finished my PhD in geography at UNC Chapel Hill earlier this year. So this work that I'm presenting today was funded through UNC, through the EPSA project. And I'm presenting today an analysis of the energy transition in Malawi, and situating it within economic and demographic transitions. So just a bit of context. This graph is not mine, but I think it's a great illustration of the trajectory that sub-Saharan Africa is on when we think about the energy transition. So this brown line here is sub-Saharan Africa, and the graph is showing the population that is reliant on polluting fuels. In sub-Saharan Africa, this is mostly biomass, so wood fuel and charcoal. So we can see there's been quite the departure from other regions of the world, and it is on a very different trajectory. So this work is examining why we're seeing this, and there has been a bit of a transition based on my analysis within the use of biomass towards charcoal use, less firewood and more charcoal use over time. Sub-Saharan Africa is very unique in that 60% of all charcoal used for household energy needs is produced and consumed in Sub-Saharan Africa, which represents much less than 60% of the world's population. Charcoal is distinct from firewood as a biomass energy source for several reasons. So one is that it's typically associated with urban populations. Urban populations are using charcoal because it lets off less smoke when burned, so people find it cleaner because it appears cleaner, though it lets off lots of harmful chemicals when burned, like carbon monoxide and PM 2.5. For this reason, it's preferable to firewood in urban populations. It's also very transportable because it's much lighter than firewood. And it's available year-round because once it's produced, it can be kept in dry bags and transported year-round versus firewood, which may be seasonal and get wet during rainy season. Another thing to note that's important about charcoal is that, especially in Malawi and some other countries in southern and eastern Africa, charcoal production has emerged as a really important livelihood strategy, and I'll show that with some of my data that I'm presenting today. And so the argument that I'm going to make here is to try to show why this is important, and also talk a little bit about the environmental impact of charcoal production and why it's important to keep a close eye on what's been happening with this biomass energy shift in southern Africa. So charcoal production is distinct from firewood, traditional firewood gathering. Traditional firewood gathering, people are gathering branches and sticks, things that are on the ground, not necessarily cutting down full trees, but for charcoal production, you need to cut the tree and carbonize the trunk, so it can be more destructive to forests than traditional fuelwood gathering. So this is why we should be concerned about this. So I'll make the case for why are we looking at Malawi as an example. Malawi is landlocked next to Zambia, Mozambique, and Tanzania. It's the 4th poorest country in the world and very, very reliant on biomass throughout both the urban and rural populations. The population is still over 80% rural in Malawi, though the urban areas are growing very, very quickly, and the population of Malawi itself is growing very rapidly. From 2004 to 2020, which is the study period for this work that I'm presenting, the population grew from 12.5 million to almost 20 million, so it is growing extremely quickly in both rural and urban areas. And additionally, Malawi lacks a strong alternative to biomass fuels. There's not really a strong ubiquitous electricity infrastructure. There's not a strong supply chain for liquid petroleum gas, LPG, as an alternative fuel. And because the population is very, very poor, traditional fuelwood gathering has primarily been the strategy to meet household energy needs. So fuel purchasing is something that can be quite difficult and constrained in this context. So in this presentation, I've done tons of descriptive analysis, modeling analysis, and mapping, and I'm going to just show you the results, and if you have questions about some of the models that I ran, I'm happy to talk about that in the Q&A or after the fact, but because this is a big, complicated story, I'm really going to just tell you what I've been finding in these analyses. So first, I'm going to show trends in fuel use in Malawi from 2004 to 2020. Then I'm going to show some of the modeling results that I found identifying what potential contextual factors geographically and in local environments are driving people to use more charcoal in rural areas. And then I'll demonstrate some potential impacts by mapping where we've seen intense deforestation in Malawi. For this study, I was using large secondary publicly available data sets, so 4 waves of the World Bank's Living Standards and Measurement Survey, Integrated Household Survey. So this was collected in 2004, 2010, 2016, and 2019. And also the global forest cover data, which is 30 by 30 meter resolution, global forest data that showed the extent of forest cover in the year 2000, as well as on an annual basis, loss of forest cover. So I'm able to quantify it on an annual basis. So integrating these data sets, I will show you a bit of what I found. So first, looking at fuel use across geographies in Malawi. Okay, so this graph here is breaking up the population of Malawi and the survey results by rural population in that left-hand column of the graph and urban population on the right. This is the proportion of households that are using a particular fuel as their primary cooking fuel. So households may be using other fuels and fuel stacking, but this is primary fuel use. And what you're seeing, so the smaller bars on each of these graphs are representing the results of each survey wave, and the rows are representing regions of Malawi, because Malawi is broken up generally into 3 big regions where you can see slightly different trends in economic and agricultural and land use phenomenon. So generally what we're seeing is that over time, we're seeing an expanded use, especially in the rural or urban areas, of charcoal. That's the black proportion of the bars. And firewood is making up a smaller and smaller proportion over time, both purchased firewood, which people will purchase at markets, or collected firewood, which households are collecting themselves. The blue is representing electricity, so you're seeing very little electricity use overall. So remember, the urban population only makes up 20% of Malawi's population. And you're seeing it fluctuate, I think, because of smaller sample sizes of the urban population in this study. But also there's been some challenges of keeping the electricity infrastructure smoothly running. In the rural areas as well, we're seeing some more charcoal use, which is really interesting because, as I mentioned, charcoal is a purchased fuel. So households who traditionally have access to collecting firewood, which is very ubiquitous in Malawi, seem to be moving more and more towards purchasing fuel. So that gives us an indicator that there's more cash income for households in rural areas being allocated towards purchasing fuel for cooking. So those are the trends. And then I spent a lot of time thinking about what is potentially driving these changes and these trends. So one kind of broad area of this is population growth. So again, population growth linked to urbanization. As more population growth is happening, there's both population growth happening in the rural areas as well as expanded urbanization. So both are happening at the same time. There's rural to urban migration, and the population overall is growing. So we're seeing these expanded consumer base in the urban areas, as well as people potentially migrating to the urban areas more and more from the rural areas because there's pressure on land use and people looking for alternative livelihoods in the urban areas. So that's one factor. Also, economic development. So as I mentioned, as people's livelihoods are generating more cash income and they're able to allocate more cash towards purchasing household fuels, we may be seeing an uptake of purchased fuels in lieu of traditionally collected firewood. Also, market access is expanding geographically. In my descriptive analysis, I was able to see that more and more rural communities had a daily or weekly market available throughout the study period. So it means market access is more ubiquitous, access to these commodities for purchase, and community reliance on participation in the wood fuel value chain, whether that's producing charcoal or producing firewood. My guess is that it's charcoal because that's a very lucrative and important livelihood strategy. And then finally, thinking about the environmental context, access to woody biomass. So we know that for collecting firewood, it's really important to have ubiquitous access to forests for people to go and gather firewood. So when forests may be deforested, when there is forest loss, people have less access to the forest to collect firewood. So in my models, I was analyzing how much the forest cover in the area around the communities, as well as the amount of forest loss, was related to rates of charcoal and firewood use. So, and this is kind of a visual example for those who are GIS users. I was measuring in this local area. For example, all that red would represent forest loss and linking that to rates of fuel use in that particular community. So I used pooled, zero-inflated Poisson regression models to model rates of fuel use for different kinds of fuel, charcoal and firewood, for 2,246 communities that were sampled through these 4 waves of data. Quickly, what I found was, as expected, population growth was promoting the use of these purchased fuels, charcoal and firewood, and collected firewood was decreasing in use as these population growth factors were positively increasing. The same is true for economic development, so greater wealth in the community and market access promoted the use or associated with more charcoal and purchased firewood use and less collected firewood use. However, it was interesting, I didn't see a relationship between communities that were participating in charcoal production and more charcoal use or less firewood use, so that seems to be unassociated in this data. And the story of woody biomass access was a little bit more complicated. So forest extent in local areas is really closely tied to firewood use, whether it's collected firewood, so in areas where more forest cover is in the area, you're seeing more firewood collection, a very strong relationship. You're seeing the opposite for purchased firewood, which is interesting. But it makes sense. If you have less forest around to collect firewood, you might have to end up purchasing your firewood. However, we did not see that for charcoal use. We did see for charcoal use in some of the models that forest cover loss was associated with greater charcoal use. And so there's a lot of mechanisms to unpack there. I wouldn't go as far yet to say as that deforestation is causing charcoal production or charcoal production is causing deforestation. There's a few things that I'd be happy to discuss in the Q&A. I didn't have time for it right now. I'll get through the rest of this and talk about it more later. But we're not seeing very clear relationships at this local level that deforestation and charcoal use are really clearly linked. So that's a summary of what I just told you. I'm going to skip this for time and we can come back to that. So because we're not seeing these environmental impacts and this close relationship between forest cover loss at the local area, I wanted to know where might we be seeing deforestation in Malawi, or if we are seeing any that might be related to charcoal use. So none at the local level, but in the descriptive analysis of these data sets, we saw an increase from 11% of rural communities up to 18% of rural communities by the end of the study period reported participating heavily in the charcoal production industry in Malawi. So we know a lot of people in Malawi are producing charcoal. And I know from a lot of my field experience in Malawi, I've been going for the past 6 years, most of the charcoal trade in Malawi is reported to be domestic. So most of it is produced and consumed within Malawi. So that leaves us the question of where is wood fuel production, charcoal production actually taking place? So I conducted an analysis mapping deforestation in forest reserve areas in Malawi. So I calculated the amount of forest loss disaggregated by time period to show some really interesting trends. And what we saw is in some large forest reserve areas that do not have timber plantation operations, these are protected forest areas, between 2004 and 2020, up to 20% of the forest area of these reserves was deforested according to my analysis. So we're seeing some major deforestation in particular forest reserve areas within Malawi, in these particular 5 areas. And then I disaggregated the trends over time and mapped them. So what this graph is showing is these 5 areas that I identified as having about 20% of the forest area lost. The darker the color represents more recently in time. And so what this is showing, there's lots of this dark orange and red. Most of the forest cover loss has happened between 2012 and 2020 in this area. So we're seeing a rapid increase in deforestation, and these patterns are consistent with people going deeper and deeper into the reserve to collect more woody biomass for charcoal production. And based on some field site visits and hearing from the Ministry of Forest officials, this aligns with what people have been observing in Malawi for the past several years. So that is the story that I've put together with all of these analyses. We're seeing several transitions influencing each other and that are linked: demographic, economic, and land use. The expansion of charcoal consumption and production has implications for both rural livelihoods and for forest management, so we need to see a more integrated approach to managing sustainable development. There's little evidence from this analysis that charcoal production impacts local forest cover, but those relationships should be explored more to understand them. And forest loss patterns suggest that these forest preserve areas have been impacted recently by informal or illegal charcoal production. So there is a renewed urgency for these integrated approaches to managing sustainable economic and natural resource management. And that is what I have for you. Thank you.
Hello, hello.
Hi, my name is Hannah. I missed the first part of the presentation, so if it's something that you said, please just clarify. So I'm wondering, in slide 6, I saw that the population in the south, in the urban, the use of electricity declined from one year to the other, and I'm wondering, can you speculate what happened?
Yeah, so there's 2 things that could explain that in the data set. One is that there's small sample size for those urban communities, so there's about 50 communities sampled per year. So you might see some bounciness with the point estimates because of a small sample size. But also, Malawi's electricity infrastructure is powered by hydropower, and that infrastructure has been not well kept and not upgraded in the past several years. So there's been some issues with power management, and it's made the electricity supply in Malawi very unreliable. And there's some evidence that people, because it's so unreliable, choose to use something that's more consistent, like a purchased biomass fuel. So that would be my guess of what explains that.
Okay. We're going to try and save time for a discussion after, so let's move on to our next speaker, which is Professor Pamela Jagger from University of Michigan, School of Environment and something.
Sustainability.
Sorry. They keep changing it. Okay. Número 2.
Okay.
Okay, well, we're getting set up. So I'm actually pinch hitting for a recently graduated, actually, human being, Dr. Nabeen Pradhan from the University of Michigan, who is the author of this work. Wrong presentation. Yeah. He's the lead author on this work, and I'm a collaborator, but we just found out on Friday morning that he wouldn't be attending, so it's been a bit of a mad scramble for me to get this presentation together, and I will, for full transparency, say that this is preliminary work, and I'm not in the weeds on the analysis. So I think you'll see some similarities with the work that you just saw presented for Malawi. here we're looking at an interesting example of another, what I would refer to as a reverse energy transition. So we hear a lot from the development community about how there are sustainable energy transitions happening throughout Africa. And when we really dig in and look at the longitudinal data that we have to bring to bear to this question, there are many examples, Malawi and Zambia among them, where we're seeing actually a transition to more cooking with biomass when we look at the population level. Okay, so I think we're already sort of in the weeds on this in thinking about how energy transitions are not as clear-cut as we think they are. We know that they're happening very successfully in a handful of places in Africa, but not everywhere is getting the same level of attention with respect to thinking about how these transitions are taking place. So without further ado, we have zoomed in on Zambia in part because our research group has been working there for the past several years. And as we've been spending time there and, trying to charge tablets for data collection and, just basically function, we've been experiencing more significant blackouts and brownouts and extended periods of power outages and talking to policymakers and asking lots of questions. And what we're seeing is that, the availability of electricity, which is the primary clean fuel for household cooking, is actually declining over time. It's very unreliable. Zambia is also a very interesting case because it has a relatively large urban population relative to other countries in Africa. So it gives us a little bit of a glimpse of maybe what the future is going to look like for several other countries in Africa. Much like Malawi, Zambia's power infrastructure is not entirely, but very heavily dominated by the hydropower infrastructure. And again, with climate change in the region, the Zambezi River Basin and the Shire River Basins have just been dramatically impacted by climate change. So there's some years where we've got floods, and that has implications for hydropower management, and some years where there's droughts. So we're looking at what trends have we observed in household cooking over, it's retrospectively roughly a 15-year period. These are the years that we have data for. I think we have a new round of data coming soon, which is going to be really interesting to look at. We're trying to understand the association between our observed increase in the use of biomass fuels for cooking and what that might mean for deforestation and forest degradation. And we think we're trying to build a body of literature where we're really looking at the dynamics of energy use and forest cover change so that we can not just think in a very cross-sectional way about what's going on. For this analysis, we use data from the demographic and health surveys, which are, I'm sure most of you are maybe familiar with them. They're population representative surveys, so they cover the entire country. They have representation for both rural and urban areas, and they ask, it's not an ideal question, they ask households what the primary cooking fuel is that's used in the household at a particular period in time. We know that households are using lots of different fuels for different reasons, but what we are able to glean from these data is what the primary fuel that's used in the household is. So you can see we deal with relatively large samples of households, but when we try to tie this type of information to spatial data, we have to operate at different units of analysis, right, to be able to tell a story about associations. Right now, our analysis is looking at forest cover loss over the 3 years prior to the corresponding year that the demographic and health survey were collected. And right now in this preliminary work, we're using a 20-kilometer buffer zone around the georeferenced cluster that's part of the DHS data set. And then we have a number of covariates that we're looking at to try and understand and control for other factors. So again, just an overview of the data sources that we're using. And I'll just credit Kate here, who's been advising Nabin on quite a lot of this analysis. So you'll see here the distribution of the clusters of the demographic and health survey data. So it's very, exceptional coverage across the country. And then we've overlaid the protected areas because we have, from our work in Malawi, we have some interesting clues about the impact of protected area management or lack thereof, right? Because it's different in different settings. So similar to the graph that Kate showed you, or the figure that Kate showed you, what we observe in Zambia, and I want you to focus in first on the urban population, which is on the right-hand side, is that we see, again, this similar trend of declining, and this is share of the population, right? So we see the similar trend of declining use of electricity for household cooking. And what this is being effectively directly substituted for is use of charcoal, and I'll show you another graphic in just a minute. We also see, again, a similar trend in rural areas that use of charcoal is increasing as well, which is a little bit, again, we were surprised to see this as we did in Malawi. So this is the framing of the story of a reverse energy transition. When we look at these things, different data presentation here, you can look at these graphs and see that it really does seem like it's a direct substitution. People are frustrated with the electricity access situation for cooking. There's a particular problem with cooking because it really requires a lot of power and everyone's doing it at the same time. So it's extremely challenging if you're, ZESCO and you're trying to manage electricity supply to make sure that there's adequate supply at these peak periods when the infrastructure is really having lots of challenges associated with it. So again, this is clear evidence of direct substitution. People are using charcoal because the clean fuel that's available to them is not reliable at all. So why do we care about this? Of course, lots of reasons: the health burden, the climate impact, gender-related impacts on women and children who are collecting wood fuels and engaged in charcoal value chains, and then occupational health concerns as well. And then, of course, we're also interested in the deforestation impacts, or we think that we should be concerned about deforestation impacts. So using the spatial data, we've done what's called hotspot, cold spot analysis. And again, this is Nabeen's work. So, and maybe Kate can answer some of the questions, but we've had a look to try and understand deforestation patterns over time. We have about 20 years of data that we're able to look at this question with. Let me see if I have a pointer here. Sorry. Oh, the red line. Yeah, okay. So for those of you who know Zambia, you'll know that this area is LULCC broadly. So we've got, some signal that maybe this urban population is in somehow having some sort of association with deforestation. The other thing that we're digging into is this area up here, and you'll see the deforestation patterns are heterogeneous across time, right? It's not, apart from this core area around LULCC, there's some sort of patchiness to it. This is an interesting spot because if you know the geography, Kisangani, which is a major city in southern Congo, is kind of like right in here. And there's pretty high demand for charcoal moving across the border into that area as well. So again, we're trying to associate these deforestation trends with the observed changes in household energy choices. So again, this is preliminary. So we've run some regressions with the dependent variable being actually the deforestation variable. Thanks. And then looking at covariates, including of course, the covariate that's of most interest to us, which is what the primary cooking fuel is in households. And then we've got a few other covariates that we're looking at that we're getting from the various data sets that we've put together. This is a regression analysis, again, still preliminary, so we're fiddling with the buffer zones and the variables that we're including in the models. But so here's some of the early results and punchline, just for interpretation. So first of all, we see sort of a clear association between these biomass fuel choices and the deforestation trends that we're observing. So the estimates are that a 1% increase in charcoal use is associated with a 0.09% increase in forest loss, all else equal. Some evidence that the wood fuel uses are also having an impact. We've split this into rural and urban because, again, we think that this is really largely an urban story, and we get, again, it seems like the urban story is driving much of the result that we get in the pooled data set. And I think it's really important to remember that Zambia's population is roughly 50% urban. So when we're talking about population representative data, it's a little bit different than Malawi, where we have these small sample sizes. We've got a pretty good set of data to draw upon. So I'm going to wrap up and say, again, that we've got, we're seeing a reverse energy transition, which is very frustrating from a macro policy perspective, and also from the micro perspective of households, right? People want to be moving towards modern energy services, and we've got some evidence that is a challenging proposition. We have this clear evidence of substitution, so I think we're going to see more and more charcoal use on the continent going forward as the population is growing, as urbanization is occurring. And as we're really sort of absent really robust regulatory frameworks for thinking about how to manage this sector. We've got deforestation hotspots that we're really going to be digging into and trying to learn much more about how those specific hotspots are associated with the fuel use trends that we observe. And some sort of early indication that there may be an association between these fuel use choices and deforestation in the Zambian context. So I think I'm going to wrap up there, and I'll just point to some obvious things, which is that we need to do something about the grid infrastructure in Zambia if electricity is the clean cooking pathway forward. There's signs that the Zambian government is actually shifting towards liquefied petroleum gas because they cannot solve this grid infrastructure problem that they have. So we need to be thinking about what the alternative strategies are. And then I think, really, I just want to say broadly that for all of the work that we're doing, Africa is so interesting because we know so much about a very small number of countries, right? If you think about the places in Africa where people are doing research, we can collectively put together the list, right? Kenya, Ghana, Ethiopia, Uganda, South Africa. There are so many places that we are not really paying close attention to, and where there's really a real potential for this kind of reverse energy transition to be taking place. So it's a pitch to do studies in the Central African Republic and other, interesting places where these reverse energy transitions might get masked by all of the positive stories coming out of a small number of successful places. That's it. Okay.
Excellent. Thank you very much, Pam. Anybody have any clarification questions? Yes, madam. Introduce yourself also, please.
Hi. Thank you so much, Pam, for your presentation. Just a clarification. You did rural versus urban to see, but have you gone further in looking at heterogeneous, like categories of household in terms of income level?
Yeah, so this is one of my questions back to Nabeen. We're using a wealth index that's part of the demographic and health survey data, and it's a very unsatisfying, because it's you're a 1, a 2, or a 3. It's an index, so it's a composite of all of these other variables. So we need to really, and we don't see anything, we see no statistical significance between that wealth index and the outcome variable that we're looking at. So there's much more work to be done. Yeah.
And you said the LPG use is negligible in the Zambia case?
So the data that we have are up to 2018.
Oh, I
so if we have another round of data, we'll see that it has increased, but it's still not very big. Yeah.
Thank you.
One more clarifying question, and then
Thank you. My name is Hannah. It's just out of curiosity, I'm wondering, when you say that forest loss due to fuel, yeah, due to energy, I wonder from the socio-ecological aspect of it, right? Are there practices, right, that follow this? Because if you see communities that are harvesting trees for charcoal, usually there's a mechanism around it, like they are either harvesting and then planting, or harvesting branches of not the entire tree, you know. And so essentially when you say that there's forest loss, when I say you're cutting down the entire tree, or you're not replacing. And the other aspect of clarification is what percent of this forest loss is actually due to fuelwood, yeah, and not other land uses like clearing land for agriculture, for example, or clearing land for building houses or something like that.
Yes, okay. So just on the modality of charcoal production in that part of southern Africa, it's what I would characterize as small-scale clear-cutting. Like, it's people typically identify a patch of this Miombo woodland forest and will cut down like 8 or 10 fairly large trees and then heap them all and produce the charcoal on that site, and then it gets bagged and transported out. So it's not deforestation like, hectares at a time. It's these little tiny patches, which in a place like Zambia, maybe it matters and maybe it doesn't. I mean, they have a relatively small rural population, relatively, right? And they have abundant forest resources. So maybe it's not that consequential. I want to be very careful to say that we see an association. So it's just a statistical relationship. I wouldn't not say that fuel use is causing deforestation. So what was the other question? What was the other question? Oh, for sure, agriculture. I'm sure agricultural expansion is far, far surpassing fuel use in terms of deforestation impacts. Yeah.
Thank you, Pam. The question is actually a really good segue, I think, into the next set of presentations, the first of which happens to be mine, and the next will be my colleague Adrian's. So these presentations are sort of in tandem. I'm going to lay out some context and be a little more qualitative and a little more high level, and then introduce a modeling tool that mostly Adrian has developed over the past 20 years, I don't know, that I've been contributing to in fits and starts as well. Let me get the clicker. Okay, so like I said in the opening of the session, my name is Rob Bailis. I'm a senior scientist with Stockholm Environment Institute, which is a global environmental think tank based in Stockholm, but we have offices all around the world, including several in the US, where I am based. Let's see. So Kate already laid out some of the context here. I'm just going to go into a few more details about it, and also because some of you weren't here at the start, so it's for your benefit. So why talk about what we're calling clean cooking? And I'll step away from the specific country level analyses and talk about the entire globe. So somewhere around 2.3, 2.4 billion people rely on polluting fuels, mostly biomass, so wood and charcoal, for their daily cooking needs. It's about a third of the world's population. As Kate pointed out, it's on a downward trend. However, in some regions, it's on an upward trend, and specifically in sub-Saharan Africa, this is the bar chart version of the line graph that Kate showed at the beginning. The number of people reliant on these fuels is projected to increase by 450 million by 2050. That's the population of the US and Mexico. So it's a lot of people. It's a lot of wood. It's a top risk factor globally for illness and death. Why? Because when you burn solid fuels in tiny little fires, you can't burn them well, and incomplete combustion causes pollution that's really bad for you. Imagine smoking, but every day inside a little closed room. So about 2.6 million deaths in low middle income countries for the year for which data is most recently available. That's maybe third or fourth top risk factor in illness and death globally, number one in sub-Saharan Africa. It also, when you burn stuff incompletely, it sends off all sorts of pollutants that are not only bad for you, but they're bad for the environment, and specifically they contribute to global warming. So we estimate about 1 to 2% of global climate forcing can be attributed to this sector. It's not a lot, if you think about all the other things, but it is a lot in the sense that, well, that's a lot of pollution, and it's equivalent to about the emissions from the country of Germany, or from the aviation sector, or from the global maritime shipping sector, so it's considerable, and it's something that we can do about it. And I'm not laying attribution, I'm not saying like the people who are contributing to this should take steps to necessarily mitigate it, but it's something that we could imagine mitigating and getting multiple wins for, health and climate. It also places a huge budget on a huge burden on household budgets or labor, depending whether people are collecting it manually or paying for it, as Kate pointed out earlier. Depending on the country, it varies. And think about it from a resource perspective, it's the largest single source of demand for woody biomass. So roughly 1 out of every 2 trees that's harvested for any reason ends up in somebody's cooking fire. So imagine all the wood that's harvested for pulp and paper, for construction, for furniture, for high-value timber. All of that, add all of that up, and then double it, and that's the amount that people are using for cooking. We think, and this is where language is important, it's a major driver of degradation, not necessarily deforestation, meaning permanent land use change from forest to non-forest, but slow loss of tree cover, essentially, whether in forest land or in other landscapes. And that's what we'll focus on for some of the talk. Boop. Okay. So specifically because we're GLP, I'm going to focus on these 2 impacts, climate forcing and degradation. The other impacts are equally important. If this was a health community, I'd talk about the health part. If this was a socioeconomic community, I'd talk about the labor. You get it. Okay, so how much degradation? We don't know exactly. We try and estimate it. This is one paper that came out a couple years back. I was not associated with any at all, but I like the graphics, and it presents a nice, concise estimate. So they did an analysis looking at different drivers and different geographies, and come up with an estimate of about 0.6 gigatons of CO2 per year attributable specifically to wood fuels contributing to degradation. What does that mean? It's a little more than 1% of global emissions, so it lands right about at the estimate that I just put out earlier. This is just the tree cover loss. And where? Well, this finds that the majority of degradation in East Africa and South Asia can be attributed to wood fuels, whereas in other regions, it's also a driver, but it's not the dominant driver. Incidentally, Adrian and I just completed an analysis globally that looks at the same, coming from a completely different kind of approach, and we find a roughly similar figure, so we're pretty excited about that. We have error bars around the R's, I didn't put it up here, but we estimate about 0.7 billion tons per year. So, not bad. Thank you. And we'll go through all well, not all, but some of the details of how we built this model in a little bit. Okay. So the title of my talk was The Promise and Perils of Nature-Based Solutions to Address the Clean Cooking Problem. So what is the promise? And it's all those things that I mentioned earlier. If you can imagine a successful intervention, whatever that might mean, then it kind of ticks all the boxes. I have up here the graphic for the Sustainable Development Goals, SDGs, and predominantly we're talking about SDG 1 is poverty, SDG 3, which is health, gender equality, Energy, the connection's obvious. Climate, the connection, well, I've explained a little bit, and I'll explain a little bit more. But really, if you give me a couple hours in ChatGPT, I could probably come up with a reasonable policy brief that makes an argument for any one of these SDGs, right? Some would be a little more tenuous, some are more direct, but you can make an argument that it touches on so many aspects. However, interventions are expensive. Globally, we estimate to meet SDG 7, which calls for universal access to clean and modern forms of household energy, including cooking, by 2030. To achieve that, we estimate roughly we need $40 billion a year in public sector investment. That's just to create the enabling environment. Okay? We need 2 to 3 more times that to pay for the appliances and fuels. And remember, these are the world's poorest people. Okay, so it's really a huge challenge. And if you look at these impact categories that I put up, health, poverty alleviation, climate is really the only one, for better or worse, that generates nearly this magnitude of funding. So that's where the promise comes in. You have all of this funding mobilized, carbon finance or climate finance, that could go into this, and with all of these potential wins, gender, health, environment, not non-climate environment. So even though that's not remotely sufficient, it's still the largest category of sort of funding mobilized globally. So we see clean cooking as a nature-based solution that can unlock funding not just for climate change mitigation, but also for generating all these other potential co-benefits, if things work out well. Okay, just a little aside, what does an intervention look like? And I kind of categorize these into 3 groups. The first, we'll look at the supply side. So if we're cutting trees too quickly, we're leading to either deforestation or degradation or some combination of the two, then let's enhance the supply. We can imagine forestry-based interventions or agroforestry or farmer-managed natural regeneration, something that basically adds trees to the landscape, whether it's a protected landscape or a working landscape. Second, we can reduce demand for the technologies that for the fuels that people are using, but keeping them using the same fuels. So basically, introduce a stove that uses a little bit less or a lot less of the same fuel. Okay, this doesn't necessarily address the health, but it will address some of the other aspects. People are just using less. Same job, using less. And also, some of these tools can clean up combustion significantly, so you maybe get a little bit of health benefit as well. Third, you can switch people off entirely, and this is what both Pam and Kate mentioned, working with electricity, or working with cooking gas, LPG, and just get them off wood entirely. This picture here is actually from Kenya. It shows an ethanol-based vending machine where you can go in with a little bottle and fill your bottle with an ethanol-based cooking fuel. And that's actually taken off quite a bit. It sounds actually quite surprising, but it's actually quite popular in and around Nairobi. Okay, so one example of an option 3, again, this is not work that I've done, but it's a great example, and it's actually one of the only ones that I'm aware of where they did a nice systematic assessment. This is looking at a very large-scale biogas intervention. That, incidentally, was funded by carbon finance. I won't talk about the details, but they found 10 years after the intervention, it was quite successful, hundreds of villages, that they found statistically significant increases in standing biomass, some species abundance, and some impact on species diversity. So great, a true nature-based solution. So excellent. What's the peril, though? Okay, I'm sort of building to this. There has to be some downside, right? So carbon finance is a fickle beast. If you follow the news around carbon finance, much of this funding, so carbon finance is basically anything that's generated to finance climate change mitigation, essentially. But most of the finance actually takes the form of carbon offsets, which, if you follow the news, have run into problems, well, off and on, but very, very much lately. So I have some headlines here, and this is from my little sector, or our little sector. There have been carbon problems everywhere, but this one is recent and generated a lot of news. So a Nature paper came out about a year ago, led to a Guardian article saying that some of the projects might be over-crediting by as much as 1,000%, a factor of 100. So that's not great, right? And then for a first that we're aware of, there's actually criminal charges against one of the major purveyors of clean cooking-based carbon offsets, who Pam and I actually know personally. It's a bad scene. And so integrity has very much been an issue. A lot of it is unintentional, so a lot of the projects that were looked at in this Nature paper just basically followed methodologies that weren't great. But then also within it, there's probably not just this guy who was caught, but a lot of bad actors. Okay, so if you're relying for one of the world's largest health environmental problems on a market-based solution with poor oversight and very complicated rules, you're probably setting yourself up for some serious challenges. Okay, what's the connection to GLP and this community here? Well, about a third of the overcrediting, of that factor of 100 overcrediting that I mentioned that was pointed out in that Nature paper and then highlighted in The Guardian and led to criminal charges in the US Department of Justice, were from overestimations of the impact of wood fuel harvesting, of the baseline, the business as usual, on tree cover. And that's where we come in. So the default assumption that many people make is that when people cut trees, they're gone for good. So if you cut a tree, that's deforestation. And that's not the case. And this is, I think, what Helen, right, was trying to get at. Trees can and do regenerate, right? And we know that. The same data sets that Kate was using that show tree loss, well, there's a big asterisk that says this is not necessarily deforestation if you read the fine print. And then there's also a layer you can add that shows tree regrowth. They also show, they say don't compare the two because they're using different methodologies. So it gets complicated. But by assuming little or no regrowth from harvesting, projects vastly overstated the impact of wood fuel consumption and wood fuel interventions. Okay, so we know it's probably not 100% of trees. When you cut a tree, it's probably not gone for good, or when you get many trees, they're not all gone for good. But we also know they don't all grow back. Particularly, it depends on how fast you're cutting, how fast the trees grow. All right, our question, and this is the research question that me and Adriana have been wrestling with now for well over a decade, how much grows back? And of course, it depends. What does it depend on? And then can you simulate that? And can you validate the simulation? And that's what we're trying to do. Okay, so how do we model this? We use 4 key parameters. They're spatial in extent. They vary in time. The first is wood fuel consumption. And by wood fuel, I mean both wood and charcoal. Who uses it? Where are they? And how much do they use? This is an example from Kenya. Then we look at tree extent and growth rates. Where are the trees? How fast do they grow? How much is there at time 0? And how much would be there under either business as usual or under some kind of intervention? How accessible are they? How likely are people to go to any one place? What's the cost in time or effort? And then are there other drivers? And this maybe gets at your question. What's going on with all those other things that cause people to remove trees? Agricultural expansion, large scale, small scale, commercial timber harvest, infrastructure expansion, all those other things. Okay. And this just shows an example of some of the work that we've done recently. Adrian will go into much more detail. This shows an example from Uganda, which I pulled up because I've been working there quite a bit recently. And the numbers are probably too small, but just this is a result. We find about 35% of the wood that's harvested now and into the near future, who's simulate going into the future, is unsustainable. So that means for every 10 trees cut, 3.5 grow back. Okay, and then we can also use that to estimate what the net emissions are and what the impact of an intervention might be. Okay, so I'll stop there. I'll take 1 or 2 clarifying questions and then pass off to Adrian to discuss some of the nitty-gritty details of the model. But I'm happy to take a clarifying question while our colleagues in the back pull up the next presentation, if there are any. If not, I'm happy to sit down also. Oh, we have a little...
Oh, yes? Okay. Hi. So I'm Adrian Gilardi. I work in the Environmental Geography Research Center in UNAM, in the University of Mexico. And there it is, Rob. So basically, I can't there's something interesting here. The model that we've been building for the past 2011, 2012, it will be 12 years now, it's too complex in the sense that it's too large. It has many parameters. So what I will do, because we have a little time, I will focus on a couple of things that might be interesting, because one of the things I believe we've been doing that put us a little bit aside from other people doing similar things at broad scale is that we were not like cutting corners in very particular issues that I would like to bring ahead. So I will talk about that, and then a little bit on what we are doing now that is pretty exciting. Okay, in any case I will put this so I can. So this is important, global reproducible model. So something important of what we're doing is that everything is open. It's open source, it's free, everybody can download it from what we're working. It's not as easy to use because it's not a software that you install in your computer. There's a lot of steps. It's more like a research tool that has been developed for the past 10 or something years. Next ones, please. No, sorry. Okay, so I will, again, give a few insights on how it works, because it has too many moving parts, but I put the effort on a few of them. Oops, sorry. So then I will update a little bit on what we're doing on the new resources and the exciting new work that we're doing now. I have plenty of extra slides that has to do with the policy implications and other stuff that in case that some questions arise, then we can step into that. So, again, it's not like a software that you install. It's a multi-language geospatial model. It uses 3 layers of coding. We use Google Earth Engine, Python, and R, and all these prepare all the data, even it's at a world scale or a local or national scale or even a landscape scale. Then it's go through a C++ submodel, and at the end it has them spatiotemporal modeling. So basically there's a lot of stuff going on. I will only focus on a few of them. Then the next one, please. I'm sorry, I'm so stupid. Okay, so I will focus a little bit on scenarios. So Rob mentioned, and K2, that for different countries we had these projections for fuelwood, rural, urban, for charcoal. So we know for many countries what are the patterns or the trends of consumption that we expect for the whole country. So what we do is that we spatialize these trends into the population map of the raster population map of how the population is distributed, urban, rural, and how this is evolving in different years. In this case, this is the charcoal map for urban plus rural just for the year 2021. So these places are where the wood is being used, where the charcoal is being burned for that particular year. Then we have for fuelwood and for the rest of fuels. What do we do then is that, and this is something interesting that we were able to build, each of these, it's called pixels, each of these places, there's a certain amount of wood that is being burned or charcoal that is being burned, and from each of them, starting from each of them around the world, 7 million around, we draw an accessibility analysis based on topography, slope, roads, bridges, rivers, you name it, a lot of stuff. For each of them, we use parallel computers, certain IA there, and so we try to build accessibility maps from where the wood might be coming from. And this is it's robust in the sense that we are picking every single place, but then it's not so robust because charcoal might come from farther away or from closer away. It's not something that you can actually model completely, but it's a very good approximation of where the wood might be coming from. So from there, what we build, we need to use very, very big computers to calculate this. So from that idea of accessibility, we build for every country in the world, or at least in the global south, maps for where the wood might be coming from for fuelwood, for charcoal, for each year during the simulation period, that in our case is 2020, 2050. So for each year, we have a seeding mechanism from where the people might be getting the wood from. That's one insight that I wanted to give. Then, what about the supply part? Where the wood, yeah, great. Still have 10, right? Yeah. So we do this in different ways, and this is something that we're working now, but basically we combine biomass maps, how much biomass do we have now, and in 2 times. We use land cover maps that we download from Google Earth Engine. We use IPCC values. We use global ecological zones. So we mix this in a way that we are able to pull different growth curves based on IPCC values, on land cover change. We're not using climate and soil here, but basically biomass. How fast the regrowth curve should look if there were no actual intervention. These are just regrowth curves that are based on time. This is something that has been worked by many different research groups. We have this approach, and this approach is what we've used for the last model, but we are replacing this, and I will show it in a last slide. So what you see here, these are just 5 random pixels out of the 7 million pixels, just 5, and these are the different growth curves that appear just randomly there, and this is how that pixel will react to the harvesting that was modeled in the previous stage. This is not so simple. It has some variation. So one of the problems or one of the critics from the carbon market and all that is that our results are too uncertain, and they want just exactly what is going to happen. That is not so easy. So there's a lot of variation, and this variation comes because the data that we are using to model this, it's already uncertain in the first terms. So what happens, this is a very simple way to show it, is that for each, this is again 1 pixel, or well, 4 different pixels, 4 different places in the world. So you may have a trend, a baseline of growth, and then depending on where that pixel is located, you may have harvest events. People will be harvesting wood for fuelwood or for making charcoal. And if that is too frequent, like in the red line, you will have a decline over the simulation period. This is just an example for you to get an idea. If you have some harvest events, but at the end you end up with more wood fuel, more biomass than was in the beginning, then well, you didn't degrade the biomass, but you might have more if you reduce those harvesting. So it's more or less how it works in temporal scale and also at spatial scale. At different pixels, this happens at different times. So this is more or less how it works. There are other features that I'm not going into. One of them is important, and it has to do with Kate's presentation because it's a submodel that models land use cover, and I will show why that's important in the next slide. No, not in the next slide, but in the coming slide. So all of the results of our research that we are intending to publish eventually are in our webpage. Rob already mentioned this. The idea is that you can query this data set, you can zoom in, you can draw polygons, for example. Let me go here and then I will go back. You can draw different polygons and get results of what is the sustainability wood fuel harvesting in different times of the period between 2010 and 2050. But something I want to mention from the previous one, sorry, this one. So something that we just finished, and I think it's going to be updated this week, so Thursday or Friday they will be up, is we have new tools for people to explore these scenarios. So a lot of people using this information from the voluntary carbon market and the cooks of intervention, they want to know things that are usually not so easy to grasp. So we're putting a couple of tools that people will be able to revise. And also, we are extending the period to 2050. This is something that we just finished. So we have the results that Rob shown are now until 2050. We have other stuff that has to do with hypothetical scenarios. That was something that wasn't before. So now we have what would happen if we have a massive cook stove deployment around the world. What can we see there? So we have some extra information that is going to be online in a few days. So how do we know that this is true or not? So it's just a model, right? It's geofiction at some point. So what we started to do in certain areas, we found that our model, it's not very good in certain areas and it's very good in some other ones. Why? Because the problem with doing a global model is that you can't tune it. Great, yeah, I'm almost finished. The problem with the global model and our exercise is that you can't really tune it for what is going on at the landscape level. So it's very difficult to integrate variations at different country regions with certain assumptions that we might take. One of those assumptions is, for example, calibrating the land use cover change submodel that assumes where the wood is coming from, if it's coming from deforestation activities, from land clearing, or if it's coming from infrastructure or urbanization. So there are a couple of things that need to be tweaked in different places, even at the global level, to get a sense that the model is working. We didn't have time to do that. So the idea now, and this is something, is get this big model that is regionalized. It's not one global model. It's a lot of regions around the world, and try to calibrate it a little bit when things that we are seeing. For example, in this case, this is just an area in Malawi, but this is the observed losses. This observed losses in above ground biomass. We don't know the cost here. We just know that this was observed between 2010 and 2020. What we're trying to see is, okay, what do our model looks like compared to what was observed. So simulated versus observed. In this case, there is no calibration at all. But we know that we have a lot of tools at tweaking things that we can make the model fit what it's being seen, so it will be more robust. So in that sense, another thing that we've been exploring is that at broad regions, I just show you a little bit in Malawi, but we have this information for many countries. So we know how biomass behaves in the past, and we try to see if the simulations of the model in the past coincide with this, more or less something like that. So this is, I'm not sure if I will be able to show the simulation. I'm good. Let me see if it plays. No, it doesn't. Can you, ¿le puedo poner enter? So this is one of the model results in the sense that this is how it runs, but this is, the message here is important. There it is. So now it's running. This is harvest, how the model project where wood is being harvested for fuelwood and charcoal. These are the trends, so each year people requires more wood, and this is how it's affecting above ground biomass. How do we know this is wrong? Because it's not happening in the time being. So from 2010 to 2020, it doesn't quite match. How can we fix it? The first thing is the land use cover model. Why? When we turn that on, instantly it goes to the places where deforestation is occurring, and then it fits a little better. Another thing, it's open the border. Now the border is closed in this example, but we have the possibility to open the border to Mozambique. So we can tune things and make this look better. This is not happening at all, no? And the idea is, this is what we are trying to work right now, trying to model the observed things to the simulated one. So look, 2050, no more trees in Malawi. So something is wrong in that model. Okay, this is some of the research we're doing. I already mentioned a little bit, but one is making all of this model run in a web-based interface so people can use it. Now it's open source, but it's difficult. So everybody can download it and run it. The documentation is very poor. It's confusing because it's a research model. So we got some funding to make it something usable in our clusters at UNAM. The other thing, this is the thing we're doing with the Nature Conservancy and Sea Trees. They have very good maps, or at least much better maps on regrowth parameters, and they already shared it with us. So we do have now information of regrowth rates that has been observed and trained with artificial intelligence by these guys, and we're trying to integrate this into the supply model. So this will give us, I believe, something less uncertain and much more robust to the ground that should be reflected in how the observed versus simulated results compare to themselves. We always need to calibrate and check that our simulations coincide what we are seeing in the field. We have these 4 very promising new places to work. One is Zambia. This just started, and it's good because we have all the information and what Pam showed. This is Kisangani in Congo, where Julien Shure is working, and she's already very interested in collaborating with us. This southern Malawi with Silvera, and here Shimoshi, this is in Uganda. So these 4 places will allow us to do 2 things. Compare the 1 kilometer model that it's being calibrated with actual simulations at 100-meter resolution. That is how all this was already built. And then we could look at the nuances and look at the details and see if at higher resolution we might get a better understanding of what is going on. 30 seconds. Woo! And the last thing that this is going to be simple. Again, the practitioners don't like uncertainty because they don't know how to use it. So we have a lot of pressure to reduce this. So basically, we're doing more runs, more simulations, because this is all computer, and we're trying to reduce this uncertainty. And that's it. I put another photo because we have new members in the team. Yeah, sorry. Anyway, thank you very much.
Okay. Thank you. Thank you for everyone sticking through our session. I dreamed of having like 15 minutes for discussion, but we have 5. It's okay. Yes, and I will just not talk myself anymore.
Hi, I'm Cole. I'm a graduate researcher at MIT in solar energy, and I'm kind of more focused on the fundamental science side of solar development. But my question is, for any of the speakers, how much data is available on uptake or use of small-scale, let's say, single-family renewable cooking fuels? And as the cost of those technologies and of implementation of those, let's say, small modules decreases, are we anywhere close for those solutions being economically viable for the average family? Or is it still, are the upfront costs of those solutions still just much too large for them to be viable?
Okay. Can I answer? So the question's really about solar, right? So I'm going to go out on a limb and say maybe nobody is cooking with solar, first of all, because the technology just can't, the energy requirements the solar technology can't support. To data on household level solar technology uptake, these population representative data sets do have relatively good data on, do you own a solar technology? It's a yes/no question. So it could be like a solar torch, like a flashlight, or it could be a robust solar home system with 8 to 10 bulbs. It's just a yes/no. We've done recently a study in Malawi, and I'd be happy to talk more with you, or Kate can talk to you about it after this. The uptake over the past decade, 0 to 20% of households in rural Malawi. They're very small systems. And it's primarily wealthier households that are adopting them. So it's not a universal access. Yeah.
Yeah, I would just add some of the national data sets, not the DHS surveys, but some of the national level household welfare surveys will differentiate between like a pico solar system, like a single little light or a torch, versus a solar home system that implies multiple lights. And there is some work going into household level cooking on solar, not cardboard box cookers with tinfoil, but integrated with panels. But yeah, the upfront cost is too much, but the running cost is 0. So if you can imagine, maybe supported by carbon finance, all those caveats, some sort of financing model where those costs are spread over a year, 5 years, for family burning charcoal, it's financially viable, but you need all of that infrastructure in place in order for it to work.
Yeah, sorry, I missed to present myself last time at talking. My name is Ida Jenote from Penn State University. So my question is for you. I was a little bit confused at some point. Can you tell us in 2 words, what's the objective of your model?
Yeah, sorry about that. You're right. That's a good question. So the objective is model is just trying to see if the wood that is being harvested for fuel wood and charcoal has any impact on the standing biomass. It's just that.
Okay, so then to clarify the unconclusive result that you have in Malawi, and then you have the opposite in Zambia as far as the correlation or the association is concerned. Or not?
Kinda, no. Because, well, there's one thing, scale matters. Resolution matters a lot. And this is a global model of 1 kilometer, and these are particular case studies.
Okay.
However, the model also ran at 100 meters.
Okay.
But basically, when we calibrate this thing at 100 meters with the information they presented, we should get very similar results.
Okay.
It's not something like divert. It's the opposite. One thing that, sorry if I'm talking too much, but is that in this model, when you clear the land, it will look if the pixel doesn't come back. If it doesn't come back, it will assume that it's not coming from charcoal. Because if it was only charcoal, it will come back. That's something that we use to see if it's charcoal or not, basically. But that's the only difference.
Okay, and then the last question that I have, how does that relate, or maybe Bailis, Rob, you can tell us, the clean cooking thing, how do we integrate that in the model? I think at some point you said any clean cooking technology could be added to the model to see,
Right.
but then which one, right? We know the different types of clean cooking technology and different performances.
Right. So I won't run back to it. I'm happy to talk offline also. But so when we run what we call our business as usual model, we incorporate data from these national surveys that say, like, this is what people are using today. We're also using projections from the WHO. Those are the things that Kate put up right away, and I put up a bar chart version of that project under the absence of new policy interventions, what they expect. So again, it's all fiction. Right? People are making this up, but they're smart people. So that's the BAU scenario. Then we can tweak that. We can say, well, what if instead of whatever the charcoal trajectory going like this, what if charcoal trajectory goes like this, and instead it's cooking gas, or it's a 50% efficient charcoal stove. So we can do anything like that, and I'm happy to show you some of the intervention trajectories that we've used on these models. Again, all fiction, but some of them are based on stated policies. For example, Kenya has a very aggressive clean cooking policy in place. Uganda is, I'm supposed to be contributing to it. We're trying to develop a clean cooking strategy for Uganda. What will it look like in 2030 or 2040? So yeah, like there's a lot of thought going into this. Of course, saying it, even if it's an official government policy, it doesn't mean much unless you mobilize the funding and you get everybody on board and you put in all those enabling factors. But yeah, so we can simulate just about anything, and we have, even building in, because we're looking at first primary cooking, but we can build in stacking and multiple households using multiple technologies. So that gets a little more complicated, but it's certainly possible. So yeah, all of that can be simulated, and we've run some scenarios where we're looking at different kinds of simulations and looking at what the impacts on land cover could be, and then what the emissions that result from that could be. Yeah. So we're kind of at time, but I would love to have Pam have the last word.
So I think your question is really good, and I just want to maybe connect the dots, which is that right now 20% of carbon credits generated on the voluntary market are coming from cook stove projects. And we have this recent set of events that suggests that who the hell knows if those are actually legitimate. I mean, they're not actually, because there's criminal charges being brought against this particular individual that generated. But there are also some good projects, right? But so the problem is the data. We need good baseline data, and then we need good data on what's happening over time so that we can actually objectively estimate the carbon offsets, right? Because if we don't have a way of doing that, then we just have to take on face value whatever these project developers are saying about what's going on in the field. And it's crushing this idea of results-based financing for the sector, because there's all of this dishonesty or not quite transparent and clear and accurate information. So, I think the vision is that the MOFIS could be used to actually verify a lot of this.
Verify is a strong word, but yeah, like we're definitely in conversations. All right, so thanks everybody for sticking through. We're around, we're reachable through the app, potentially. All right, thanks.